So, now we are going to discuss the yarn formation, the structure and applications of friction spun yarn. We have already discussed a bit about the yarn formation of drape 2 yarn, which is basically a kind of open end, which is produced on the basis of open end principle, and we have discussed about them earlier. Now, in drape 3 yarn formation, we all know that it is basically a core sheath type of structure, and therefore, it is not really open end spinning. It is more close to basically wrap spinning. Now, here two groups of fibers meet at the yarn formation zone. One group is fed by the drafting unit 1, that is by the pair of roller drafting rollers, and the other group is coming from the top, that is basically opened by the opening rollers, and then they are actually landing on the surface of the friction drum, and friction drums, a pair of drum is actually the twisting element of the spinning machine. So, the strand of fiber from the drafting unit 1, it flows and it reaches the nip of the friction drums, and the friction drums are actually turning in the same directions. So, that at the nip area, the two surfaces of the drum rotates or moves in the opposite directions, and the fibers which are coming from the drafting unit 1, this set of fibers initially get twisted by the two drums. There are internal suction in the drum, the fibers get stuck on the drum surface, and as the surface moves, the bundle of fibers which is resting on the drum surface will be twisted. But as I said earlier also, this twist is basically false twist. Now, so therefore, at any point of time, what we will find that the fiber bundle coming from the drafting unit 1, they are basically twisted along the entire length of the drum. But once they move out from the drum, the twist is going to be lost, because basically it is a false twist. Now, fibers from the drafting unit 2, that is coming from the top, they will be landing on the friction drum, and the drum surface will carry them forward near the yarn formation zone, where already some fibers already exist, that is the core fibers already they are existing there in the form of it, in a twisted state they are existing there. Now, the one issue that we should know, that as the fibers land on the drum surface, the fibers get buckled, because their approaching velocity is much more than the velocity of the roller surface. So, most of the fibers which are ultimately going to form wraps, they get deformed by the time they are landing on the surface of the friction drum. But that we can't help, though people are trying to somehow straighten the fibers by properly designing the transport channel. But whatever we do, ultimately fibers at a higher speed are actually landing on a slot speed surface. So, there is going to be some amount of buckling and loop formations or deformation of the fibers, which will be finally wrapped around the core. Though, therefore, now these fibers are actually approaching a torque field. It is a field because the entire drum surface is acting as a twist generating mechanism. Therefore, over the entire length, the bundle of fibers are getting twisted and also getting wrapped. So, wrapping is done basically on a false twisted core. Now, as soon as the fibers moves out, both the core as well as the wrapped sheath fibers, the core fibers will suddenly turn in the opposite direction, because they have to release the twist. The torque is there because the core is false twisted, and in doing so there will be a lot of interaction between the two group of fibers. Some of the false twist will be removed, but entire false twist which is there in the core fibers may not be removed, because they remain trapped by the sheath fibers. Sheath fibers are already existing on them and trying to grip these fibers, the core fibers. Therefore, even though the core fibers is experiencing an untwisting torque, it may not be able to still the entire torque may not get removed from it, and therefore, sometimes we expect that the core fibers in the case of drape 3 type of structure, where there is a core and sheath, some twist may be still left in the core. The core sheath ratio is usually maintained at the level of 50-50, it could be 60-40, or at least 30% sheath fibers are required in order to produce a yarn which will give you a reasonable strength and elongations. So, usually it is 50-50 or 60-40 or 65-35, that is the typical core sheath ratio, and maximum people go up to 70% core, 30% sheath, but is never 80% core and 20% sheath. In that case, the yarn is going to be very, very weak. Now, we will discuss about the structure of both the yarns, drape 2 and drape 3. Drape 2 structure, as I said earlier, it is basically the principle of spinning is based on almost basically on the open end spinning principle, because there is no core filament or core fibers we are introducing. There is no drafting unit 1, there is only one drafting unit where fibers are opened out by the opening rollers, and then they are released on the friction drum. Now, here there is one concept that has been proposed, that it is like a stacked cone, that the fibers are actually getting wrapped, and they are actually existing on the surface of a cone, as if the fiber is forming a conical surface, each and individual fibers, and the yarn is a stack of series of cones. That means, fiber is existing at the center, the same fiber will also go at the surface. So, automatically people may feel that there is some kind of migration like ring spinning, that if the same fiber is existing in the core and again the other part of the fiber is existing at the surface of the yarn, that means there is a migration. So, if there is a good migration, one would expect good strength, but drape 2 structure never gives you a strong yarn, and it has been found that these yarns, if you put some load on it, the yarn will fail, and the failure is because of the slippage of fibers. If the fiber slippage is the primary mode for yarn failure, that basically means there is some absence of interlocking between the fibers. If the interlocking is not there, there cannot be gripping action between the fibers. Therefore, it has been seen also that we can propose that the crisscrossing or intermingling of the fibers does not exist. The fibers are actually is in the form of a cone, another fiber is also following a conical surface, and if we have a stack of cones one after the other, the yarn will look uniform, but if I pull them out, the entire fiber will move out, because intercone migration is not there, and hence these yarns are basically very, very weak. The other proposal is something like this, that it is basically in the form of a coaxial helices of various or varying radii with little interlayer migrations. By studying the fiber configuration in the yarns using tensor fiber techniques, this also has been found that the way the twist varies, that it can also have a structure something like this. That is, as it is shown here, you see that there is quite a few coaxial cylinders are there, and if a fiber is moving around this cylinder, then and if the cylinders are there one after the other, that overlapping each other, then there is still may not be any migration between the fibers. That is, the fibers are not really crisscrossing. A fiber is following a helical path of uniform diameter. A fiber which is there on the yarn surface, it is following the helical path of the yarn diameter, maximum diameter. A fiber that exists at inner layer, it is also following a uniform, a helical path having uniform radii. If the radii of the path does not change, that means there is no migration. From layer to layer migration will not be there, and if it is not there, then there is no gripping between the fibers, and therefore, if I pull this bundle of fiber, twisted fibers, the yarn will fail. So, even though apparently it will look like lot of twist is there, but still the yarn will fail because of slippage of fibers. So, that has been seen by some people after studying the way studying the helix angle of the fibers using tensor fibers, and it has been shown that helix angle decreases from outer layer to inner layer. The average twist remains fairly constant across the layers. So, if the twist remains constant, the twist angle, which is the helix angle, will keep changing from outer to inner. There is another opinion by Stalder and Solomon, where they are also proposing that because of the varying yarn diameter and fiber migrating from rotating slip to non-rotating yarn tail. See, this I have not really discussed, but there is another theory, or you can say an idea given by these two researchers, that there exists a sleeve between the two drums, and this sleeve rotates, and there is a yarn tail which exists within the sleeve, but this yarn tail is stationary, is not rotating at all, and the fibers are actually moving from the inner surface of the sleeve to the non-rotating yarn tail. If the sleeve rotates and tail is stationary, the fiber will be wrapped, because what we need is relative motion. So, in this case, the tail of the yarn which is existing within the sleeve is non-rotating. It has only a translational motion, that is, can only move forward directions, because we pull the yarn out, but the tail is not rotating. It is the sleeve that exists between the drum, which is larger in diameter and rotates at a speed depending upon what is the diameter of this and what is the frictional contact it has with the drums and what is the drum speed. And from the sleeve, rotating sleeve, fibers are actually transferred to the non-rotating yarn tail, and hence the yarn tail is not uniform from the delivery end to the opposite. See, if this is the sleeve tail exists like this. And fibers from the inner wall of the sleeve is passing over it. And the sleeve is only rotating in something like this. So, this is the yarn tail is moving out, it is stationary, and from the inner wall of the sleeve the fiber. The sleeve is forming by the fibers which are fed from drafting unit 2. There actually the fibers are landing on the drum and they are forming a kind of rotating cloud, a rotating sleeve, and the rotation of the sleeve actually is causing fibers. Somehow the sleeve is not very smooth, it is consisting of large number of fibers, and therefore, from the inner surface of the sleeve fibers coming into contact with the yarn tail. Tail also has some projecting fibers. So, somehow they get cut by the fibers projecting out from the yarn tail, and once they are cut they start getting wrapped. That is how the twisting process is going on. That is what has been proposed by these two researchers, and that paper is also published as it is shown here. And what they say, if I am rotating the fibers around the yarn tail, wherever the diameter is less, rotation will be more, wherever diameter is bigger, rotation will be less, and therefore, twist will be varying. So, because of the varying yarn diameter and fibers migrating from rotating sleeve to non-rotating yarn tail, the twist in the core is greater than on the yarn surface. So, twist fibers which are getting wrapped over here, that twist will be more. See, this fiber will gradually move. So, at different point of time it is wrapped here, then this part is coming over here, then this part is coming over here, then this part is coming over here, because it is continuously moving. So, the fiber, therefore, the yarn tail is tapered. On the delivery side it is coming to the dimension of the yarn, but at the other extreme end it is thinnest, and the thin portion keeps on moving forward, and it is receiving fibers continuously as it is travelling through the sleeve length or across the length of the friction drum. That is how this kind of theory also has been proposed, and based on that they are saying something about the way the yarn twist will vary. So, there are different types of ideas have been proposed by different researchers, and we need to know them. The yarn failure, now based on these two, if we see that whether it is this way, whether it is a overlapping coaxial helix, or it is basically overlapping of conical yarn or conical structures. If there is no interlayer migration, there is no gripping between the fibers, and therefore, there is hardly any strength that will get into the yarn. So, therefore, since interlayer migration is limited, frictional interaction between the layer will be too weak, and irrespective of the structure type, the yarn would fail primarily due to slippage of fibers. That is one of the greatest weakness of drape 2 technology. So, in the case of drape 2 technology, if we want to enhance the yarn strength, the only way that is left with us is to introduce a strong filament in the core. That is only way. So, if we want to produce certain yarns where the load bearing part of the yarn is the filament that exists in the core, and we want to surround the filament, we want to cover the filament by some other fiber due to some other reasons, because maybe we want to have a good sensation of touch. Therefore, the sheath fibers has to be maybe cotton or maybe viscose rayon or something, but the inner fibers could be, these filaments could be many other, maybe carbon fiber, maybe Kevlar fiber, maybe very strong high tenacity polyester filament. Depending upon the need of the product, we can have some strong filaments there, and it is generally preferred to have multifilament yarn than monofilament, because of what will be the problem if we have a monofilament then wrapped by cotton or wrapped by polyester fibers, staple fibers, or maybe polyester viscose staple fibers. What will be the difficulty that we will face after the yarn has been produced? There will be slippage. Yes. The interfacial interaction between the filament and the staple fibers are not very good, not very strong, and therefore, usually we find there is a slippage of the sheath fibers or fibers which are wrapping the filament core. This is a typical problem. They can easily slip on the core, and that may lead to some kind of difficulty during the formation of, during winding of the yarn subsequently, or during the formation of the fabric also. So, that difficulty could be there. So, this is one of the problem of this particular technology, but there are different people have tried different ways to solve this problem also. That is, they have given the yarn the heat treatment, and through that maybe some kind of bonding is created between the filament and the staple fibers. In some situation it may work. Then if we go to drape 3 structure, it is a basically core sheath type of structure, where there really exists a core. The sheath fibers are helically wrapped over the core and exhibit generally jet twist. Sheath fibers belonging to the different feed fiber positions lie in the form of overlapping layers. So, that diagram is shown here. See, from this side, from the upper side, these are the 5 slivers, sliver 1, sliver 2, sliver 3, sliver 4, sliver 5. Usually 4 to 6 slivers are placed, and all these slivers are simultaneously they are opened out by the opening roller, and the fibers belonging to these slivers will then move downwards and will land on the friction drum. Therefore, the fibers coming from sliver 1 will be wrapped over the beginning part of the at the entry level, at the entry part of this friction drum, and then this, as this moves forward, it will go from position 1 to position 2, the same fibers, and now on the position 2, as it goes there, fibers from the sliver coming from position 2 will be wrapped over the fibers which came from position 1. Now, the fibers, yarn containing fibers 1 and 2 will move to position 3 now. So, from whatever fibers are coming from position 3, they will be now going on the top of the fiber layer 1 and 2. So, like that, the fibers will be deposited on the top of each other. That is quite called the overlapping of fibers, overlapping layers will be there one after the other. The helix angle and the helix diameter of the sheath fibers originating from sliver position 5th to 1st reduces progressively, because by the time the fibers are coming over, fibers are falling from position 5, it is actually going over a larger diameter of the yarn. And we can expect also that this diameter is rotating at a slower speed than the diameter here. If this is A, this is B, the friction drum surface speed is fixed, constant. So, when it comes to diameter B, diameter is larger, so rotational speed will be less, where in diameter A rotational speed will be more. So, fibers coming from position 5 will be wrapping, that wrapping rate will be little slower. Therefore, the twist we can expect to be different. Helix diameter will be more because the yarn diameter is gradually increasing from A to B. At A the diameter is minimum, at B the diameter is maximum, because layers are getting built up one on the top of the other. The twist remains more or less same irrespective of the sheath sliver positions. This also has been found that this really does not make much of a difference in the final twist. The sheath fibers have less twist than the core fibers. Core fibers mean the fibers in the core part of the yarn. So, the cross section part of the yarn is shown in the same diagram. The orange part is the fibers belonging to the sheath, and the gray part is the fibers which are forming the core. So, core fibers are actually coming from the drafting unit 1, that is roller drafting unit. So, they remain in the core and they all get false twisted. Sheath fibers have less twist than the core fibers. So, this also has been seen that, as I said, in some cases these twist may remain trapped, though theoretically or ideally we would expect entire false twist to be removed, but practically it has been seen that some twist remains trapped, and at some zones are there where the sheath fibers may show less twist than the core fibers. See, whatever is happening here is very complex, because there is a possibility of slippage also, which we have not yet discussed, because these fibers are not really positively gripped by the rollers. So, while they are rotating at a high speed, and the only force that is acting and pushing the fibers towards the drum surface is a pneumatic force. Now, this pneumatic force may not be sufficient enough to avoid slippage between the when the fibers, the drum surface and the band of fibers which are there. There is every possibility of lot of slippage, and the yarn, as this rotates on the drum surface, keeps on jumping also. It is not that always it is in contact, sometimes it loses contact because of a lot of centrifugal force which is acting between them. A lot of air turbulence also gets created there. So, all of these basically means that there is a possibility of the yarn tail losing contact on the drum, and therefore, there is a lot of slippage. So, twist leakage is also there, and hence many people also have shown that, and this will be true also for drape tools, because ultimately fibers are gripped not between the rollers, like in the case of ring spinning, we grip the fibers between the front roller of the drafting system, and that grip is very powerful grip, and the other end we are inserting twist. So, there is no scope for the fibers to lose twist there in the case of ring spinning. There is no scope, because the other end of the fibers can never rotate, they are so powerfully gripped, the tail end of the fibers in the twist formation zone, or the yarn formation zone, not twist, yarn formation zone. But here it is not so, the slippage possibility is always there. the yarn surface is more akin to the conventional ring spun yarn. The two diagrams are shown here. You see the especially the chiffon polyester in sheath, the surface looks quite smooth like a ring spun yarn. The other one is cotton on the sheath. So, the wrapping is not so good, because cotton fibers are there are fibers of different lengths are there, or polyester fibers are uniform length. So, if I wrap it with polyester, the yarn surface will look much more uniform and lustrous, whereas if I wrap it by cotton, it may not be that. There is a lot of hairiness also can be seen because of the nature of the cotton fiber. The other aspect of the structure is the core fibers exhibited both straight and twisted configurations. The core fibers exhibit both straight and twisted configurations. That basically means the fibers remain straight for a part of its length and was then false twisted in the remaining length. That means part of the fiber sometimes can be seen without having any twist. A fiber is how long it is. Suppose a fiber is 38 millimeter, 48 millimeter. So, one can see some fibers in the core partly twisted and partly straight. This is all because while untwisting, some twist has been removed, some still has been left out there, and hence this kind of fibers will be visible. Majority of the fibers had a single direction of twist, that is either Z or S. Now, the existence of Z and S direction twist automatically means that the entire false twist could not get nullified. Some of it remains trapped. So, Z and S twist therefore can be seen in the core fibers, and few core fibers are also seen having both direction of twist Z and S, but there are few. Majority are basically either having Z or S twist. So, ideally we expect the core to not have any twist, but in actual case some twist is still there. In a way, this twist is going to in a way help also, because it is going to give some amount of binding between the fibers. So, the yarn, it will make the yarn stronger. So, drape 3 yarns are much stronger than drape 2 yarns. Influence of process parameters. First of all, we will discuss about friction. Generally, high fiber to fiber friction enhances yarn strength, especially this is true for drape 2 yarn, and drape 3 yarn also it will happen, because ultimately it is basically a structure where core is practically twist free, we can say, and it is wrapped. So, ultimately if we can increase the friction between the fibers, it is going to resist the tensile deformations, and therefore, there will be some strength enhancement. High fiber to metal friction enhances twist efficiency, that slippage will be less if we can go for fiber to metal friction is more. Fiber strength will always increase the yarn strength. It is true for any yarn technology, yarn spinning technology. Fiber fineness. Too fine fibers may lead to too many hook and loop fibers in the yarn, that is too many deformed fibers, because finer fibers are basically having very little flexural rigidity. So, they can easily bend. Coarse side, therefore, we go, but we have to also remember that friction spun yarn needs more fibers in the yarn cross section, so that we can spin the yarn successfully. If we go for, so there is a critical minimum number of fibers that we need in the cross section to make sure that spinning is feasible or spinning process is stable. So, that minimum numbers of fibers is much more. Suppose for ring spinning it is around 80, for rotor spinning it will be 120, 130, for friction spinning it will be still more, maybe 160, 180. So, we cannot go for too coarse fibers, then number of fibers in the cross section will go down, and therefore, the cohesion between the fibers will be low and will not be able to spin the yarn successfully. So, too coarse is not possible. At the same time, coarse fibers will not be able to wrap it, because for wrapping also we need fibers to bend. So, if the fibers are too coarse, especially sheath fibers, they will not be able to bend properly and they will not make tight wraps. Length, this is the range. Long fiber has a tendency to lap around the opening roller. This is something one has to be careful, and long fibers get easily deformed. So, too long fibers are not really beneficial. At the same time, too short fibers also would not be good. So, we have to have a critical fibers, some range of fibers as given 32 to 60 mm. Within this range, it is going to give you good quality yarn. The other process parameters which are important are, one is friction ratio. Friction ratio is what? Is the ratio of surface speed of the friction drum divided by yarn delivery rate. Yarn delivery rate. So, the ratio of these two is friction ratio. So, twist is found to increase with the increase in friction ratio, but this is more significant for coarser yarn. There is a minimum friction ratio 1.5, below which spinning will be difficult. So, some ratio, typically 2 or 2.5, these are the typical ratio that we maintain in order to spin the yarn successfully. In drape 2, tenacity, extension, twist first increases with increase in friction ratio, reaches the optimum and then decreases. That means, initially with friction ratio twist will increase, and twist increases, tenacity also will increase. If tenacity increases, extension of the yarn also going to increase. But when the friction ratio goes beyond optimum, then everything will fall down. Why? Because of typical that obliquity effect. Too much of friction ratio means too much of twist. Too much of twist means too much inclined the fibers are with respect to the yarn axis, and therefore, the strength will fall. In drape 3 yarn, tenacity increases with an increase in friction ratio up to 2.3, thereafter remain fairly constant. That means, if I plot typically friction ratio versus tenacity, let us see. For drape 2 yarn, we may get a curve something like this, typical twist strength curve. For drape 3 yarn, we will get a curve something like this. So, this is for drape 3, this is for drape 2. That means, in the case of drape 3, unless we have a certain friction ratio, we will not be able to start spinning operation at all. And then there is a slight rise, but then fairly remains constant over a wide range of friction ratio. It hardly changes, the tenacity does not change much, it remains fairly constant. The structural consolidation improves with friction ratio due to improved wrapping by the sheath fibers. As a result, packing density will also improve, the breaking extension also will increase. See, the core fibers extend more before rupture. See, generally whatever we do, most of the time you will find that if I change any process parameter, and if due to that tenacity increases, extension also will increase for any yarn, whether you take any technology, any process parameter that means it improves the tensile property in general. So, tensile property means includes both extension and the breaking load. So, if I do something, play with the process parameters, and if I find that tenacity is going to increase, you will also find the breaking elongation has increased. Both of them will go up together. If the structure becomes strong, it will take more time to break. So, it will have more extension simultaneously. That is what will generally happen in most of the cases. Influence of core-sheath ratio. Here also there is a optimum. Tenacity and breaking extension usually increases with an increase in coarse percentage up to 70% and then falls thereafter. So, the point is that how a drape 3 type of structure where core and sheath is there, how the fibers in such a structure is actually participating in sharing the load, that what is important. It is the core fibers which are practically straight are going to support the load, because they are more or less straight, but it is the sheath fibers which are wrapping the core, and these fibers are actually trying to develop or generate transverse pressure on the core, and by that it is increasing the frictional resistance to slippage of the core fibers. Now, if the core fiber percentage increases, we can suppose we start from 40%, 50%, 60%, if we go keep on rise, because my load bearing fibers numbers is going up and up, and therefore, strength will rise. So, initial rise in tenacity is because of increase in coarse content, and that is because increase in the number of load bearing straight fibers, while the decreasing part is because the core content has gone beyond optimum. Now, the sheath content is going down. So, there are less number of sheath fibers to generate sufficient transverse pressure, and hence even though there are more core fibers are there, they are actually slipping. That frictional resistance to slippage has gone down, and therefore, the yarn as a whole is going to fail at a lesser load. That means, we can also expect here like this, if this is the core-sheath ratio and this side is tenacity, then also we can expect some a curve like this. It will increase first and then will start falling, and this may be the optimum, maybe this is 70 to 30. Beyond that it will fall. So, why it is falling this side? Because core-sheath component has reduced too much, and it is not in a position to generate sufficient transverse pressure on the core fibers, and therefore, core fibers as a whole are actually slipping when the load is given to the yarn. Breaking extension also will give you similar sort of behavior. The core-sheath ratio has got nothing to do much with the evenness and imperfections of the yarn. Next, another important parameter is suction pressure. The whole purpose of suction is to make sure that the fibers which are at the nip of the two friction drum they remain pressed against the friction drum. And now, the friction drum can really, the surfaces of the two drums can really generate frictional force on them and thereby torque, frictional torque on the the accumulated fibers which are there at the nip. So, with the increase in suction pressure, yarn strength is likely to increase, because we can expect more twist to be generated, less slippage will be there. And at the same time we can see the yarn diameter to reduce. So, that is a indirect reflection that fibers are held together against the drum with a higher force. Therefore, there is better packing of fibers in the yarn, and a reflection of that one can see in the diameter of the yarn. So, it gives an indirect indication that force must have been more, and that is why diameter has reduced. A higher suction pressure causes a higher restraining force on the fiber assembly, which are pressed more firmly against the friction drum. This will increase friction between the two, the torque on the fiber assembly resulting more twist, and more twist basically means more strength. So, that is how the this can work, but if I want to increase suction pressure, that means I am actually consuming more energy also. Now comes the applications. There are varieties of applications of the yarn that we can produce on friction spinning 2 or 3, that is either open end type of friction spun yarn or a core-sheath type of friction spun yarn. And this is possible because we can actually engineer the yarn in a better way, that we can selectively place the fibers wherever you want. This possibility is less with other technology. We can have a multiple component in the yarn cross section, and can we rightly place them wherever you want to place the fibers. This opportunity is relatively less in the case of other technology. We can also spin core spun yarn or ring spinning technology, that is possible. Here also we can spin core spun, but we can then wrap it better, wrapping it by not just one type of fiber, but different types of fibers also we can wrap it. If we need that, we need different fibers and different layers, we can wrap it by different fibers, different layers. Introducing a filament is much easier. We can introduce not just one filament, we can multiple filament. Filament of 2 types also can be introduced simultaneously. So, flexibility is more, and therefore, industrial applications are more. The other reason of industrial application is that we will see that limitation of the technology, and we will discuss about them. So, backing fabrics for printing, belt inserts, electrical insulation and hoses, filter fabrics, filter cartridges for dry filtration, well filtration, for sugar industry, paper industry, secondary carpet backing yarns can be produced. In the carpet backing yarn, most of the time what you use is jute yarns. So, it can be also, we can use this technology and produce yarns and use them as carpet, because we basically need thicker yarns there. Friction spun hybrid yarns made from twist free glass filaments, aramid fibers, carbon fibers for new textile preform in fiber reinforced plastics in automotive industry. These are high tenacity yarns for military tents, truck types. High tenacity because the filament that we can introduce could be of very high tenacity polyesters or high tenacity nylon can be given. Friction spun yarns with a glass fiber, continuous filament core and staple Kevlar sheath fibers can be used for fire blockers. So, a combination of Kevlar and which other one, Kevlar and glass. Cut resistance fabrics, then clutch and brake linings for automotive industry. Safety point of view, heavy protective garments, industrial gloves, industrial aprons, heat proof gloves, shoe covers, etc. Protective garments made from drape 3 core yarns with super strength filaments. So, outdoor textile, leisure and sportswear, laterally elastic corduroy or flat fabrics produced by the use of elastomeric filaments. So, there are a lot of scope for the use of the yarns that we produce on these technologies, and most of them are basically, you see whatever examples have been given, they are all basically from technical textile point of view. In the domestic textiles, tablecloth, upholstery fabrics can be made, fancy yarns can be made also, though technically it is possible we can make it, but in practical terms we do not produce domestic textile using friction spun yarns. We will see that why. Properties, if we check in general terms, we can say tensile strength, a comparison has been made with respect to ring spun yarn, rotor spun yarn and friction spun yarn. Tensile strength lower than ring and rotor spun yarns. But if we go for introduce a filament, then it can be stronger than rotor spun yarn also. Evenness good, it is satisfactory over here. Imperfections are quite high with the twist formation zone, a lot of disturbance are there, lot of air current, air vortex, these things gets created. So, fairly high. Hairiness is also high, snarling tendency is very high. That is one of the negative points of friction spun yarn. Stiffness similar to rotor spun yarns. Twist structure inhomogeneous with ring yarn like look in absence of symmetrically formed wrapper fibers. It gives a look which looks like a ring yarn, that is look wise. Fiber extent and orientation poor than ring and rotor spun yarns on the surface, especially for drape 2 they will be poor, because most of the fibers will be hooked and looped. In drape 3 also, you look at the surface fibers, most of them will be hooked and looped, because they are falling on a slower moving surface. In general properties are the yarn resembles ring spun yarn look wise. Surface is smooth when wrapped by synthetic fibers. Tenacity wise inferior than ring and rotor yarns. Yarn can be made stronger by introducing strong filament. We have to take the help of filament to make it strong. Evenness is good and hairiness is little low, provided we maintain the process parameter, some combination of process parameter. If you optimize properly, it can give you a good, reasonably good quality yarn in terms of evenness and hairiness. And it has a high snarling tendency, it can highly twist lively. The advantage and disadvantages: high twist insertion rate, drum to yarn diameter ratio is 100:1. So, if the drum speed is 3000 rpm, typical speed is 3000, the twist potential is 3000 into 100 3 lakh revolution of the yarn, that is possible. How much revolution is there in the of the yarn for ring spinning? Hardly, maximum 20,000, 22,000. Rotor spinning, how much could be rotation of the yarn? So, the speed of the rotor around not 2 lakhs. Maximum is 1.2, 1.1, that is the maximum. Here potential is 3 lakhs, but it has a potential, but actual is less because there is a slippage phenomena. Speed of the working element will be low, hence low wear and tear. Low axial tension at the yarn formation point, because there is no balloon. Within the rotor also there is a small, the yarn arm actually forms a balloon, but here there is no balloon at all. So, tension, the spinning tension is very, very low, therefore, end breaks will be very low. Possibilities of dust extraction, because suction is happening at the yarn formation point also. High delivery speed. Delivery speed is independent of yarn fineness or yarn count, because if the count becomes finer, the rotational speed of the yarn will increase automatically, and therefore, the twist will be maintained. You need not to adjust twist. Finer yarns are smaller in diameter, hence with change in fineness the yarn rotational speed changes for same circumferential speed of the friction drum. Otherwise, in the case ring spinning, if we want to go from coarser to finer count, or then we know that the twist is going to change, and therefore, we have to again change the delivery speed in order to adjust the twist, but this is something which is not required here. Multi-component structure for specific need can be produced, multi-component, that is additional advantage here. Disadvantages: high number of fibers are needed for the trouble free spinning and suitable for coarse count only. So, this technology is suitable for coarse count. Poor fiber orientation, low yarn strength, high air consumption, and increasing delivery speed causes yarn to be uneven. Delivery speed anyway is very high. So, one has to also find out what is the optimum combination of friction drum speed, delivery speed, and suction pressure. These are the three main process parameters which we have to find out what is the optimum combination of these three for a given yarn count and given fiber. Unnecessarily, if we go for increasing delivery speed in order to increase the production rate, the quality of the yarn may suffer, which is true for any technology. For any technology, there is always an optimum combinations, and beyond that, if we try to go in terms of delivery speed, then the quality of the yarn will suffer. It will be more uneven, more thick and thin paste will be generated, or more hairiness will be there, all sort of problems will be there. So, there is always a upper limit of speed, delivery speed for each and every technology. So, limitations: finer count cannot be produced. Number of fibers in the slip present between drum reduces, causing the appearance of holes. These increases the chance of the yarn tail losing contact with the slip, thus leading to high end breakages. This is a reason that has been given by someone. Finer count, typically maximum yarn count which is produced is up to 18 any. Beyond that, generally most of the counts which are produced are 6 count, 8 count, 10 count, 4 count. Production cost is high because the machine is very, very costly. and yarns are twist liably. Snarling tendency is quite high. So, either you have to go for then twist setting, which means additional cost. You have to go for twist setting. So, these are the limitation. It is not suitable for fine count, not cost is high and it is twist liably. And it cannot compete with the other established technologies in terms of cost. And therefore, we cannot spend 30s count, 40s count or on this technology. If we spend, the quality of the yarn will be much inferior comparison to ring spun yarns. So, alternative technologies are there, they can produce a better yarn when it go above this. And therefore, these technologies are mostly suitable for industrial yarns, where it is not very it is not very price sensitive product. Whereas, if you want to penetrate the apparel market, yarns meant for apparel use, that market is very price sensitive. A little increase in price, people will refuse to buy. If we want to produce specialized yarn, which we cannot produce in other technologies, especially for industrial use, then this is the technology you have, because in the products are such that price of the products are anyway very high in case of technical products, and therefore, this technology will suit that, and you will be able to produce certain structures or certain fiber combinations, which you will not be able to make in other technology. Example of vortex spinning technology, it is not suitable for coarse count at all. So, you forget vortex count, you forget air jet spinning, you cannot produce. Suppose I want to produce 4 count yarn for a technical applications, where I need strong coarse yarns. Now, what is the alternative we have? Air jet spinning? No. Vortex spinning? No. Rotor spinning? Coarser, but very coarse is difficult also. And then introducing a filament in the in rotor spinning is also very difficult proposition. Now, the only alternative is ring spinning now. Ring spinning we can produce 6 count, 4 count also, but then this will be the yarn where if we want to mix different types of fibers, carbon, glass, Kevlar in the core, surrounded by some FR viscose or FR polyester, then this technology will be very suitable. And I know the cost is high, but people will be ready to pay this cost, because these are basically meant for specialized products, for technical products. And that therefore, these technologies are the yarns are going in such in this kind of applications it is going, and that is the end of this today's lesson. So, we have discussed about the structured part of the yarn formation mechanism, the applications as limitations, and we see that structure there are still sometimes there is a lot of differences of opinion are there by the researchers, and therefore, what is generally true, that is what we need to grasp. Where there is a difference of opinion, it could be there in the researcher, because the researchers also study the subject or carry out experiments with different fibers and different maybe produced on different types of machines, the process parameters are different, and therefore, there could be some differences in the results that they get. So, individually they may be correct in their assessment of the results and drawing conclusion out of it, but possibilities of differences in the opinion or differences in the observation also could be there, because many a times they are not going to study the entire spectra of the parameters change. related to fibers, related to processes, and therefore, the complete picture sometimes we do not get. Okay. With this we will close today's lesson. Thank you.